Today we will discuss the definitions of a rotational, irrotational flow, and then one-dimensional, two-dimensional and three-dimensional flow. Here you can see the definition of a rotational flow. Okay. A rotational flow is the one in which the fluid particles rotate about their mass centers. They rotate about their own axis while flowing along the streamlines. Okay. Such a flow is known as rotational flow. The fluid particles during the motion of a fluid rotate about their CG point, that is the mass center, or they rotate about their axis passing through the CG. This is called rotational flow. So motion of a liquid, this example can be like motion of a liquid in the rotating tank. Okay. It's simple. Motion of a liquid in your domestic mixer grinder, okay, is a rotational flow. Okay. More mechanical application can be like flow of a fluid through the boundary layer which is formed over the solid surface. Okay. Inside a boundary layer, the flow has a viscous effects. It is a viscous flow. So there is a presence of a shear stresses inside the boundary layer. So that is viscous flow. The viscosity is dominant, so that results in a generation of a shear stresses, and that results in rotation of the fluid particles inside the boundary layer. Next is the definition of a irrotational flow. If the fluid particles do not rotate about their own axis while moving in the direction of the flow, then such a flow is called as irrotational flow. Okay, it's exactly opposite to rotational flow. In this, the fluid particles do not rotate about their CG point, about their mass center, about their axis. Such a flow is known as irrotational flow. Example is flow of a liquid in an emptying wash basin. Right. Example can be the flow above a drain hole of a stationary tank. The flow above the wash basin, the drain hole of a wash basin, is an irrotational flow. Okay, then we define something called 1D flow, that is one-dimensional flow, two-dimensional flow, and three-dimensional flow. Okay. Classification of the types of flow. So what is one-dimensional flow? It is the type of a flow in which the flow parameter, like a viscosity, like a velocity of a flow, is a function of time and any one space coordinate, say x coordinate. Okay. Such a flow is called unsteady 1D flow. Okay, unsteady 1D flow. Velocity is a function of a time and any one space coordinate, let us say x coordinate. Okay. If it is a steady 1D flow, then velocity is not fluctuating with respect to time, that is steady, but it is fluctuating with respect to one space coordinate, like a x coordinate. That is a steady 1D flow. So the variation of velocity is the flow parameter, like a velocity variation along the other two mutually perpendicular directions are negligible, are not present, like v component and w component are not present. Okay, so mathematically we can write u is a function of velocity component u is a function of x and t. So one space coordinate and time. So this is unsteady 1D flow. For a steady flow, u is a function of only x and not with respect to time. The other two components v and w should be 0. Okay. What is the example of 1D flow? The example can be the flow in a pipe with average velocities, with average flow parameters. Okay. You can consider this as a channel through which certain fluid is flowing with some velocity capital V. Okay, this is a channel. And let us say we have a coordinate system x and y. And let us say there are two sections, section 1,1, section 2,2 along x direction. So at section 1,1, the velocity magnitude is 30 meter per second and it is average. So with respect to y, the velocity is not varying at a section 1,1. It is average 30 meter per second. And at section 2,2, the velocity magnitude is suppose 150 meter per second. Right. So with respect to x direction, the velocity has changed from section 1,1 to section 2,2. But at section 2,2, along the y direction, velocity is not changing. It is taken as average. Right? This is an example of a 1D flow, one-dimensional flow. Similarly, we can define two-dimensional flow. So in a 2D flow, the velocity is a function of time and two rectangular space coordinates. Let us say x and y. Okay. For a steady 2D flow, velocity is independent of time and it is a function of only space coordinates x and y. The variation of velocity in third direction is negligible. It is almost equal to 0. So w is equal to 0. So velocity is a function of x and y. So u is a function of f1, some function f1 of x and y coordinates. And if it is not a function of a time, it means it is a unsteady, it means it is a steady 2D flow. Similarly, v velocity is a function of x and y. Okay. Example of 2D flow is the flow between parallel plates of a infinite length, infinite extent, flow between parallel plates. So its a flow is passing through this parallel plates of infinite extent. Let us say x and y are the coordinate systems. So at a given section, the velocity variation is parabolic. So it is varying with y, parabolic. And when you change the section, the velocity further varies with x also, and is also varying with y. So parabolic velocity profile. Then we have three-dimensional flow definition. It is the type of flow where your velocity flow parameter is a function of all three space coordinates, that is x, y and z. Right. It may be a function of a time or it may not be a function of a time. Example is flow in a converging diverging pipe. Converging diverging pipe where the velocity profile is cubic in nature. Okay, thank you. We'll stop now.